So the last thing we were talking about is we were doing the isotopes. And if we go ahead and we take a look here, I talked about how to name them. Let's just do some quick practice on these. So if I go to the notes here, so I'm at the top of page 13 right now in the notes. You'll probably see one or two problems like this on the first exam. Possibly on the final even. And so these are probably about the easiest questions that we get. And that's just how many protons, neutrons, and electrons are there in these guys, assuming that they're neutral. You saw how to do this in Chem 120, and we just reviewed it. So let's just do some quick practice. So for A, let's do the symbol. Let's do the number of protons. So P for protons, number of neutrons, and the number of electrons. Usually write E minus for electrons. And so for A is 81 Br. How could I make that symbol even more helpful? I could also put in the atomic number. So what's the atomic number for bromine? Make sure you don't confuse it with barium. Bromine is 35, yeah. So if you're looking at the periodic table, it's 35. And that number is the same as the number of protons. I don't know why I wrote it over there. Oops. There we go. Sorry. So the number of protons is 35. Good. Let's skip to number of electrons. Since there's no charge, there's nothing up here, right? Since there's nothing there, then that means the number of protons and the number of electrons are the same, right? So there would be 35 electrons. What if there was a minus here? Then how many electrons would there be? 36. Yeah, remember a negative charge means you add an electron for every negative. But there isn't, so we don't need one. Now, how do we do the number of neutrons? A lot of people will make a mistake and say 81. Yeah, exactly. It's since 81 is protons plus neutrons, and that's protons, you just subtract. So it's going to be 81 minus 35, which would be 46. Good. So 46 is the number of neutrons. Y'all okay on that? Good. And if we did 133 cesium, or cesium 133 is the correct name, first thing you would do is always look it up on the periodic table. So cesium is element number 55. So number of protons is 55. Again, there's no charge, so you would have 55 electrons. And this would again be protons plus electrons, called the mass number, minus the, what's it called? The number of protons, the atomic number. So 133 minus 55 is 45 plus 33, which is that 78? 78? Good. Are we fine on that? Good. And then a similar question. Let's say we have an element with, or an isotope that has 92 protons, 146 neutrons, 92 electrons. Without looking at anything, what can we immediately tell? Without even looking at the periodic table. It has 0 charge because it's got the same number of protons and electrons. Now what do? We look on the periodic table and see that it is 92 is uranium, right? So we have uranium. And then the most common mistake is people then write 146 up here. And it's not 146, it's what? It's going to be, this number here is going to be 146 plus 92. Protons plus neutron. So 146 plus 92, which is 238, right? Good. So that's where we got 238. And if you were reading it aloud, you would call that uranium 238 or uranium 238. Okay. Any questions about that? No? Are we all confident on that? Great. Let's go back to my PowerPoint here. And a lot of the rest of what we're going to be talking about in this chapter is pertaining to things about the periodic table. But before that, I just want to revisit some definitions that are useful. So we know that atoms are joined together very frequently when they're not together by bonds. What are the two types of bonds that you should be familiar with already? Covalent bonds and ionic bonds. Very good. So covalent bonds and ionic bonds. So the way that we get covalent bonds are atoms share electrons. And usually they're trying to achieve what? They're trying to satisfy the octet rule. Good. And we'll talk more about the octet rule in chapter 8 when we get to it again. But hopefully you remember that was the driving force, was the atoms getting 8 electrons around them. With covalent bonds, when atoms join covalent bonds, in most cases, they form what we're going to call molecules, which are discrete units of atoms that are covalently bonded together. What kinds of atoms usually covalent bond? Atoms which are nonmetals, but we will see certainly exceptions to that this semester, although it gets a little tricky as far as those go. So that's the unit that we get are called molecules. If you remember, we can represent molecules on paper as what? There's many ways to do this, but probably the best way is as one of these. So for carbon dioxide, it would look like this. What am I drawing here? A Lewis structure. Very good. Which again, we'll revisit in chapter 8. And we'll get much more complicated much more involved than we did in 120, because we'll start talking about exceeding the octet rule and things like that. But for right now, so this whole thing is a representation of a molecule. All right. So assuming they don't bond infinitely, like forever and ever, like in diamond you would have carbon making 4 bonds to another carbon, which is making 4 bonds to another carbon, which is making 4 bonds, et cetera, et cetera, et cetera. Then the word molecule doesn't really work. We'll come up with a different term at that point. But for the most part, that's how we represent them. Ionic bonds are the other types of bonds that we deal with. And to keep it as simple as possible, an ionic bond is just a conglomeration of attractions between ions of opposite charge, okay? So for example, if I have a metal with a nonmetal, sodium bonding with chlorine, they're going to form ions. Ions have opposite charges in that case. And so some of them will be positively charged. We call those cations. And we have some negatively charged ones called anions. Please, no cations and no anions, okay? And those will have an attraction between them called the ionic bond. There's not really a symbol that we use for those. Whereas we use straight lines for covalent bonds, we don't really use a symbol at all for ionic bonds. So this should seem familiar from last semester. I have a sodium atom here and a chlorine atom here. These dots represent their electrons. What do we call these kinds of electrons that are in the outermost shell? Valence electrons. And what do we call this shell? It's called the valence shell, right? Metals, as we said, like to get rid of electrons, valence electrons. Nonmetals like to gain them until they have 8. So here, when sodium loses a valence electron to chlorine, we get sodium with a positive charge and chlorine with a negative charge. How are they going to feel about each other now? The sodium and the chlorine ion are going to be attracted to each other, and they will form an ionic bond, okay? But ionic bonds are a lot more complicated structurally. We could call this the unit, because for every one sodium, there is one chloride. That would be true. But what they do is, instead of forming pairs like this, they form a more complicated structure that we will call a crystal lattice. So you'll notice these big green spheres, if this is sodium chloride, they represent chloride ions. And these little purplish spheres represent sodium ions. Now, although I've got a little circle right here saying that that's a unit, would it be just as correct to say that that sodium belongs to the chlorine above instead, or belongs to the chlorine below? I can't really say that, one sodium belongs to one chlorine. So in a crystal lattice right there, what we're just doing is we're showing the 3D representation of how these all work. They do not make molecules. So it's not correct to say that that's a molecule. Okay, it's a crystal lattice. Where does the formula come from then? NaCl looks like it's one sodium and one chlorine together, but it's really not one sodium with one chlorine. It's just the ratio. If I took this whole crystal and I counted them up, there would be as many sodiums as there is chlorine. It would be a 1-to-1 ratio. You agree that's more convenient than writing sodium 1 billion, chlorine 1 billion. Okay. So we always write ionic compounds in the lowest whole number ratio. You'll notice that these are kind of cubic structures, right? And when you look, so you can't see these individually. They're way too small, the atoms and the ions. But if you look at individual grains of salt, their structure is also somewhat cubic, right? That's not because there's little elves that are, with little hammers making the sodium chloride crystals nice little cubes. Okay, that has nothing to do with it. When you crush sodium chloride, it naturally breaks off as cubes because the underlying structure of the lattice is cubic. Okay, we see some molecules or conglomerations of molecules have different shapes, like, for example, water molecules when they bunch together to form snowflakes. Snowflakes generally have how many sides? Anyone know? 6. Yeah, they usually look like they have 6 points or 6 sides. And that's because the underlying attractions between water molecules arrange the water molecules in 6. Although we will review this later, does anyone remember that a type of attraction that holds water molecules together? Hydrogen bonds. Very good. Hydrogen bonding. Good. So what holds the hydrogens and oxygens together? That's the covalent bonds. But what holds one water to another water? That's called a hydrogen bond. So chapter 10 will review that, the intermolecular forces. So if that doesn't sound familiar, we'll deal with it then. Any of you had bio by any chance? No? Because they should talk about hydrogen bonding in bio too. Does that sound at all familiar? No? All right. It's really, really important. Now, ions come in a couple different forms. The types of ions I just showed you are called monatomic ions. In other words, just one atom, and that's it. But we also have lots and lots of polyatomic ions. And if you went to the handouts page on Canvas and you looked at the list of, what's it called? The flashcards, the third set of flashcards was a list of polyatomic ions whose names you should know. So I'm sure have heard of these: nitrate, sulfate, phosphate, acetate, etc. All right. So instead of saying which atom lost the electron or which atom gained the electron, we just look at the total formula and assume somewhere an atom lost an electron or gained an electron. Which one did it? Chapter 8. You'll know the answer. Okay. Maybe. You won't know when it happened, but you'll know who has the extra electrons and who doesn't. All right, so the polyatomic ions themselves are always held together by covalent bonds, but then they join together to form ionic bonds. So one of the ways we could look at this is we represent covalent bonds with, what's it called? Lewis structures. But with covalent bonds, it's a little more complicated. I couldn't find a really good picture, but let me see what I can find here. But if I look at ammonium nitrate, this is about as good a picture as we're going to get. So the cube is reminding us that if it's an ionic compound, it's forming a crystal lattice, okay? And we study those a lot in chapter 10. This is called a unit cell, so to speak, of these things. But what are these lines in between the spheres or the atoms? So what do the lines between them represent? Specifically, covalent bonds. Good. So these lines are covalent bonds. What is NO3 called? NO3 minus? Nitrate, good. And what is this guy here? This is NH4 plus. So this is ammonium. So these are covalent bonds right here. And again, we don't have a special symbol here, but what kinds of attractions are there between the ammoniums and the nitrates? Ionic. Okay, so we don't have a line or any kind of special figure, but these are ionic bonds. And why? Because nitrate is negatively charged and ammonium is positively charged. Okay. And off the top of my head, ammonium nitrate is probably the only compound I can come up with that has only nonmetals in it and yet contains ionic bonds, because ammonium is an ion and nitrate is an ion. So any questions about that? The reason we're introducing this, and I keep saying in chapter 8, in chapter 9, etc., is because there's really no way I can get all the way to chapter 8 without talking about molecules at some point, okay? Or talking about ions at some point. So that's why we always assume we've already had 120, so that I can say, well, you have a basic idea of what these are. In 130, we're going to go much more into depth into what they are. Okay. We know that elements are listed in the periodic table of the elements. This wasn't just randomly designed. It was designed in a very specific way so that it can communicate a lot of information to us. So can anyone tell me at least one thing that you can get out of the way the periodic table is designed that you remember from Chem 120? When I see an element in such and such a place, it tells me such and such. Can anyone answer? Give an example. Yeah. Good. I know that there will be gases. So one thing that's useful about this is columns. Elements in the same column tend to be similar. Good. So that's one of the ways that this is useful. What else can we get out of it? Yeah.
The further right you go, it's more electronegative.
Very good. The further right you go, it's more electronegative. That's something we'll talk, which means when atoms are joined together in bonds, electronegativity tells you who's going to want the electrons more, right? Good. Does it tell you anything about electron configurations? Does that sound familiar? Electron configurations were 1s2, 2s2, 2p6. What does it tell you about electron configurations? Well, all the elements over here, what do we know on the periodic table? They all end in S. So like these all end in S1, these all end in S2, and these guys all end in these P's, yeah, and these all end in D's, and these all end in F's. Does that sound familiar? So the periodic table tells me that. We'll review that also. Does it tell you anything about size of atoms? Yeah, what do you know about size if you remember from 120? As you go down a periodic table, the atoms tend to get bigger, and as you go to the right, they tend to get smaller, which seems strange, but yeah, they get smaller as you go to the right. So the periodic table is structured so that we get a lot of useful information. Some people have to be discontents and don't like the periodic table, so we also have all kinds of other periodic tables out there. Like, for example, this one. Are there alternative periodic tables? Yes, there's lots of them. So this is a cool periodic table here. Although one of my students' response to this was, this just makes my head hurt. Okay. And I can get that. But they think this is a better way of representing the periodic table, or it's better at looking at certain properties. They like this. Some people like this one, okay, or this one. I'm not going to zoom in on those, but you can look at those if you want to, just by Googling. But there's some people that have them as literally three-dimensional. You cut them out and they're like spirals that stack on top of each other. So there's all kinds of different formats. But you will not get those on. Oh, I never saw this one. That's really cool. So anyhow, but for right now, we're going to stay with the periodic table that we already love and are familiar with. So that's the structure. What do we call rows in the periodic table? What's the word for rows? The more specific word for row? Periods. Good. So elements in the same row are said to belong to the same period. In this particular scenario here, hydrogen and helium are the only elements in period number 1. So we always number these as we go down. So this row is period 1. The row from lithium to neon is period 2, etc. So as of now, we have how many periods in the periodic table? They're numbered over there. We have 7. Okay. If one of the theoretical scientists out, well, actually, no, they wouldn't be theoretical, but if they are able to make element 119, that would start period 8. As of now, last time I checked, there is no element 119. Okay. What do we call columns? Groups or families, yes. I like the term group better. Some of the groups have special names, and we can see that here. So group 1, not including hydrogen, are called the alkali metals, and you need to know that term. We will refer to that a lot. So lithium, sodium, and potassium, rubidium. Can anyone name a chemical property that these all share in terms of reactivity? They all are what? Anyone know? Extremely reactive towards, for example, like water, okay? If you put these in water, they will immediately react and produce hydrogen gas. And if they give off enough heat, because hydrogen is flammable, the hydrogen will usually catch fire and burn, especially potassium and anything lower. There are videos online of these reacting with water. The one with cesium, I don't quite believe. I think someone just dropped dynamite in a tub and blew it up or something. But they're very, very explosive out towards water. And so that's why we call them a group or a family. They have similar trends. Alkaline earth metals, also a lot of similarities. I often consider beryllium just kind of an honorary member because we don't talk much about beryllium. Sorry, but it gets left out a lot. The noble gases are all over here. At room temperature, these are all gases. Noble implies that they are non-reactive. And in fact, until the 1960s, none of these had ever been able to be made to react. Helium and neon have never been able to react with any element. I'm not sure about argon. Krypton and xenon definitely can be made to react, but only under the most extreme conditions, like very high pressures, and only with the most reactive elements. The most reactive elements are the most electronegative ones. So which two are those, if anyone remembers? Fluorine and oxygen. Yeah, fluorine and oxygens are the only ones. Like xenon, I know can react with fluorine and oxygen, maybe chlorine, but I'm not sure. Okay. That's kind of a novelty. So anything that these things do react with, because they're so stable by themselves, what does that probably mean about the compounds? So if xenon does react with fluorine, the stuff that you get is extremely explosive, okay? Because the xenon would like to say, go away to the fluorine and just go back to plain old xenon, all right? Nasty, nasty stuff in terms of explosives. For groups, we can number them in a couple different ways. And if you look on the wall, they are numbered both ways. The newer system is to number them from 1 to 18, as you see there. That's not really as useful for us. Number from 1 to 18 that's actually somewhat helpful when you get into more advanced inorganic chemistry beyond this class, and where you start not looking at the octet rule, but the rule of 18. Which explains how a lot of the elements in the middle of the periodic table react. We're not going to be doing any of that, so we will not look at the 18 electron rule. For us, we're going to be much more interested in the numbering system that you see along the top, where we have A's and B's. And really only A's. So if we look like on the periodic table I have on the screen here, 1A, 2A through 8A, that will be very useful for us. What do those numbers tell us? What most important piece of information does it tell us? Yeah, the number of valence electrons, right? So for example, nitrogen is in group 5A, so it will have 5 valence electrons. That will be very useful for us when we're trying to draw Lewis structures, okay? The ones that end in B, we don't see them on the screen here. So elements 3 through 12, but over on the periodic table, that will not have any use for us whatsoever in this class or in Chem 140. Inorganic chemists will find a way of doing it. And you'll notice it's kind of weird because look at column 8, 9, and 10. Those are all 8B. Okay, there's a reason for that. It really wouldn't make any sense for me to go into it now, but there is a reason. So, in terms of other terminology, so we've already said you want to know these names: alkali metals, alkaline earth metals, halogens, and noble gases. We don't include hydrogen on the list of alkali metals because hydrogen is we haven't defined the term yet, but hydrogen is a non-metal, okay? Except we think in the core of Jupiter that it is actually a metal, okay? Who knew? Are we going to be doing any research on the core of Jupiter? No, we are not. So, but astronomers have evidence that it is a giant metal, that the core of Jupiter might be a giant metal ball of hydrogen. Okay. On the periodic table, all the groups that end in A, 1A, 2A, 3A, 4A, all the way through 8A, these are collectively called the main group elements. The elements, so these are, if you remember, electron configurations that end in what? Electron configurations that end in S or P. Those are the main group elements. These guys, as it says here on the table, these are called your transition metals. Transition because they are the transition in going from the S to the P side. They're there. And these guys technically belong here. You'll notice the numbering. This is 57, that's 72, so these fit there. So those are called the inner transition metals. This periodic table shows a little bit better how they fit in. Some periodic tables do this in a weird way. They put a blank space there, and then they put lanthanum down there and actinium down there, or actinium down there. We will have almost nothing to say, sadly, about these elements. They're kind of specialist elements. Some of them are very useful for certain things that we need. Like, for example, europium. How many of you have ever even heard of europium? Probably not, but europium is important for LED lights and things like that. So, but other than that, we won't really be looking at too many details. Other names. If an element group doesn't have a name, like for example, 5A doesn't have a name, right? You just call it the nitrogen group. So then what would group 4A be called? The carbon group, and group 3A would be called the boron group. 6A is technically called the chalcogens, but you can just call it the oxygen group, and I'm happy. Some people give copper, silver, and gold their own name. You don't need to know this, but what are copper, silver, and gold historically all used for? For coins, because they, as we will find out later, they have a very low reductive potential, which means they tend to not react. Is that useful for a coin? Do we want a coin reacting? No. That would be bad, right? Because if you take a gold coin in the ocean and it reacts with water, you no longer have a gold coin. So none of those metals are very, very reactive. What's even less reactive? Does anyone know? Next door, but less reactive than gold is, and even more valuable, platinum. Okay. I suppose that could be used for coins. People are talking about that's a way to get out of the debt crisis, is make one big platinum coin worth like $2 trillion. Okay. Of course, you want it to be legal tender because someone who steals it would now be worth $2 trillion. Okay. Anyhow, metals and non-metals. You'll notice that the periodic table has a dividing line down it. When I sent that to my friend Jim to make that particular periodic table, I messed up. I don't think we know if a line belongs there or not. I just assumed a line would belong there, but it's no big deal. No one cares. What's the main point of this stair-step black line? It is to divide the metals from the non-metals. Who technically belongs over on this right side? That's over here. It's hydrogen. Hydrogen really belongs over here. And some periodic tables even put it here. Or they put it both there. Okay, that's fine. I'm not going to. But to the left are the metals, and to the right are the non-metals. And in a moment, we will talk about the ones that are right along the line. With the exception of aluminum, those are going to be called the metalloids. Good. So let's talk about metals. So metals, again, all elements except for hydrogen on the left, they tend to have certain properties reasonably in common. Most metals are malleable to a certain degree. Malleable means you can easily shape them, like with a hammer, for example. Think about aluminum. How are you most familiar with aluminum? What are the two ways that you're most familiar with aluminum? Foil, that's the one I wanted. Good. And maybe cans as well. But if you're familiar with a foil, you know, do you think it comes out of nature as foil, as flat sheets? No, it certainly doesn't. You can take a big blob of aluminum and it's reasonably soft and you can flatten it out. Okay. If a person is malleable, what does that mean? That doesn't mean you can pound them with a hammer and, you know, that's murder. Okay. A person who's malleable is someone who is, what's that? Flexible, easily convinced. Some people might say naive, but naive implies a negative connotation. But malleable kind of goes with the flow. You can influence them. Okay. Gullible. Yeah, I said naive. I should have said gullible. Yeah. But again, that's a negative word. It should just mean, you know, sometimes they just go along to get along. Okay. They are ductile. By the way, malleable, that varies. Some are very, very malleable. Like, for example, the alkali metals, lithium, sodium, and potassium. You can cut them with a butter knife. Okay, so, you know, can you cut iron with a butter knife? No, definitely not. So there's degrees of malleability. Gold, you can bite with your teeth and it leaves an indentation. So gold is quite malleable, but not as malleable as the other guys. Okay. You could probably cut sodium with your teeth, but again, it would make your mouth catch on fire, so I wouldn't advise it. Ductile. Ductile means the metals can be drawn into a wire. The best mental example for this is think of Play-Doh. You've all played with Play-Doh as kids. Play-Doh is malleable because you can take it and go squish, 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 and it gets flat like a pancake, right? It's also ductile because you can take Play-Doh and you can roll it up. Same general idea with metals. You can roll them into very, very fine strands, which are our wires. What kind of bonds hold metal atoms together? Because clearly they're, if you look at a copper wire, and that's all copper atoms, something has to be holding them together. Is it ionic? No, because the coppers are all neutral. Is it covalent? They're all metals, so it's not covalent. So there has to be another type of bonding that we will talk very, very briefly about in chapter 10 called, what would you name it? If they're all metals, you're going to call it metallic bonding. Yes. So metallic bonds, basically, as we'll discuss them later, is the metals, they have all their nuclei, but their valence electrons, and we'll talk about this later, so you don't have to worry about it. They're spread out around all the atoms because remember, the metals like to get rid of their electrons. So we say that they're the cations floating in a sea of electrons. And since they're floating in a sea of electrons, that is why you can easily push the metals around. They're floating around. So you just push them into a flat structure if they're malleable, or you draw them into a wire. Can you do that, for example, with a diamond, do you think? Is a diamond going to be malleable? No. And a diamond is made up of what element? Carbon, a non-metal. Good. Can you draw a diamond into a wire? Certainly not to my knowledge. You can draw them into a nanotube, but that's a totally different thing. They tend to conduct electricity and heat. Why electricity? Well, as I just mentioned a second ago, if the metals are seas of electrons, you can make the electrons move around. We'll talk about that later. Same thing with heat. You make the electrons move around, and that's how you get heat. They tend to be shiny, lustrous. Not all equally shiny. For example, iron doesn't tend to be super shiny, but gold, very shiny. Mercury, very shiny. And it turns out they're all solids at room temperature except for mercury, and mercury is a liquid. Gallium, Ga. First of all, what is room temperature? If someone doesn't say otherwise, what temperature in Celsius do they mean? Anyone know? 25, good. So gallium melts at 29 Celsius. So that means it is a solid if it was floating in the air, but if you were holding it, you're warmer than 29 Celsius. You're all hotter than room temperature, I hope, right? Okay, otherwise you're dead. So it would melt in your hand if you held gallium. Cesium, same thing, except cesium is so reactive, it would catch your hand on fire too. So you wouldn't ever want to hold it in your hand. But if it was in a test tube in your hand, it would melt. And metals, as we probably remember, like to be positively charged ions. You almost never see a negatively charged metal ion. Non-metals are pretty much the opposite. Non-metals are much more diverse in terms of their states. So some of them are solids, some of them are liquids, some of them are gases. So does it even make sense to talk about gases being malleable? Are you going to try to hit a gas with a hammer? No, good luck, or draw it into a wire? No. Carbon, as we already said, is not malleable. It's not ductile. Carbon as graphite, another one of its forms, if you try to hit it with a hammer, it just breaks into dust. Sulfur, same thing. It's brittle and just breaks into dust. So they are not malleable usually. They're mostly poor conductors of electricity and heat. And we use the word insulator for both of those. And as I said, fairly diverse in terms of the states. And in reactions with metals, unlike metals, non-metals prefer to gain electrons, which means they want to be negatively charged, not positively charged. And they do bond with each other, but they share electrons. So sulfur, for example, if it's going to form an ion, its charge will always be negative. Okay. In chapter 4, we will talk about oxidation numbers, which can be positive, but charges for nonmetals are always going to be negative or neutral. Metalloids are the ones that can't make up their minds, okay? Because they're right along the bridge, they have properties of metals and nonmetals. So here's a pretty comprehensive list: boron, silicon, germanium, arsenic, antimony, and tellurium. And how do we figure that out? Well, we look at the line and we go, are you to the left or to the right of the line? If you're on the left or the right, you are a metalloid with only one exception, and that is aluminum. Aluminum is definitely a metal. But silicon, metalloid. Germanium, metalloid. Arsenic, metalloid. Antimony, metalloid. Tellurium, metalloid. I'm not going to count polonium and astatine because polonium is radioactive, so it doesn't really make sense. It is a metalloid, but we're not going to work with it. Astatine is probably, I think it is the rarest non-synthetic element in existence. Calculations show that if I was to look at the entire planet of Earth right now, there are 5 grams of astatine on Earth, okay? And they're not all together, you know, so we're not all going to go on a scavenger hunt and find the 5 grams. There's going to be like, you know, a picogram, not even a picogram here and then a little bit here. And so this implies that it's formed by radioactivity, okay? And itself is radioactive, which means it comes into existence, it lives for a little while, and then it becomes a different element through a nuclear reaction. So we're going to ignore astatine. I'm sorry, astatine, but we will not talk about you. You may go read about it on Wikipedia. I think I actually got this wrong because I said AT. No, that's right. AT. AS is arsenic. Okay. Any questions? Anyone know what germanium and arsenic are very, very good for? If you've had physics, you should know this. Because they are in the middle, they are very useful in a set of devices called semiconductors. If you've ever heard of transistors, okay, they're vitally important. Or computer chips. You find them, they're very important, along with what other even more important element with computer chips? Silicon. Yeah, okay, good. Not to ever be called silicone, okay? Silicone is not silicon. All right. Now we're going to talk about one of my favorite subjects, but everybody else goes, ugh, I hate this subject. Sorry. And that is naming. So a brief review. This is mostly my Chem 120 notes on naming, but cut down quite a bit. Now, when you guys covered naming in 120, how long do you think you spent on it? One day only. I was going to say, yeah, I would hope 2 plus a lab, right? Okay. What I would normally spend 3 hours on in 120, I'm probably going to only spend about 45 minutes to an hour on, because again, I'm assuming you've seen it. It's not a very fun subject to talk about. And whereas it gets like a huge number of sections in Chem 120, this is really only one section in Zumdahl's textbook. And you'll notice this is 26 slides for just one section. So it's a fairly big section, but I'm going to go pretty quickly through this, assuming that you already know it. The way we talk about it in this class, in this book, is we're going to talk about it slightly differently than the way we did it in Chem 120. The organization, and this is just the author's way of doing it, the author decides to break down naming into 3 types of chemicals. First of all, these are all binary chemicals, which means binary means 2. So you should only see either 2 elements or 2 types of ions. There will be some slight deviations from that, but for the most part, you should see two elements or two types of ions. So examples of compounds, you don't need to write these down, that you cannot name. So let's look at some compounds you cannot name. You couldn't name, for example, this compound as of what we're going to do because of why. Yeah, there's 3 different nonmetals, and we're only going to worry about these type 3 compounds, which are 2 different nonmetals. We can't exceed 2. Okay. We also won't be able to name this compound in other words, you might be tempted to call it tricarbon octahydrogen or something like that, octahydride. But anything here that's based on carbon, you can't name because these are called organic compounds. Anything based on carbon that contains only carbon and hydrogen, or carbon and hydrogen and other things, they have their own special naming rules. Anyone know the name of this by any chance? Hank Hill likes this compound. It is propane. So anyone else know any other chemicals that end in ane? Methane, good, so natural gas. How about you at your gasoline tank? Octane. Yeah, so those have their own naming rules. And also we'll get into compounds like this. We'll be making this semester. This is called a coordination compound. This will have its own set of naming rules as well. Okay, because now we have a metal bonded to ammonias. So those all have their own different systems of naming. I'm going to get rid of them because I don't want to distract you. So you already should know how to name all of these. Plus, I'm going to separate out acids. You've named some acids. Can you name a couple acids for me? What's that? Acetic. Acetic, yeah. Acetic acid. Anyone else? Hydrochloric, hydrofluoric, nitric. Now, the problem with the acids is they kind of overlap. They're kind of, some of them are type 1, some of them are type 3. So I'm going to consider the acids separately. All right. So before you can do anything, you must know that there are some metals which only make one kind of charge, and you need to know which ones they are. The nice thing is the vast majority of this can be found just by looking at the periodic table. All the metals in group 1, you have 2 choices. They're neutral, in which case they aren't a compound, okay? But if they are in a compound, they will always have a +1 charge, always. So if ever I say potassium ion, you would say potassium's in group 1, it must be K+, okay? No exception that we're really aware of here. Group 2s, I'm leaving out beryllium because we're not going to really talk much about it, but pretty much everybody else definitely must be +2. The only reason I leave out beryllium is because sometimes it's kind of weird and it will make covalent bonds. So I just don't mention it. But if I did, it would be +2. The group 3s, I don't count boron because boron is a metalloid, but it's more like a nonmetal than anything else. So I'm leaving out boron, but aluminum and gallium for sure are always going to be +3. I'm never going to talk about indium, but if it's going to have a charge, it's almost always going to be +3 because it's in group 3. Thulium, and I don't even know if I'm naming that right. There's thallium and there's thulium, and I can't remember. No, thallium is, see, this is how often we talk about thallium and thulium. So one of them is thallium, element TL, who cares? Okay, so we'll just leave it at that. I think it's +2 and +3, so I'm not going to worry about it. Okay, so those are the easy ones right there. Group 1 or +1, group 2 or +2. Group 3, if I talk about it, it's going to be +3. And it's a metal. There are 3 other special ones that you have to know by memory: silver, zinc, and cadmium. The book, for some reason, calls these type 2, meaning that they can change their charge. It is highly unusual for silver to be anything other than +1. It is very, very unusual. I'm not even aware of anything where zinc is something other than +2. And less important is cadmium. Cadmium is almost always +2. So we will call those type 1 cations. They are cations that only can make one charge. All right. And the thing is about these, if someone says potassium ion, you know it's +1. If we pick a different metal like copper, and someone says copper cation, you can't do that. Copper can be +1 or it can be +2. So those are going to be the type 2, the ones that can be at least 2 different charges, and you have to be specific about the charge. Okay. Some books might include other cations. The only other one that might go on this list is nickel. Nickel is almost always +2, but I don't want you to memorize that. Okay. Let's skip to anions. Anions, you can use the group number to figure them out as well. So if you look at the periodic table, all the halogens are going to be 1- whenever they form ions, always. How do you figure that out? It's the group number -8. So 7 - 8 would be -1. Yeah, good. The oxygen group, those group 6, so oxygen, sulfur, selenium, and tellurium, those are always going to be -2 as ions. Nitrogen is much rarer, but if it ever forms an ion, it's going to be -3. And same thing with phosphorus, phosphide, it's going to be -3. And group 4 is exceedingly rare. C4- would be carbide. Yeah. Why don't I include tin and lead there? Yes, but the big difference is, unlike carbon, what's the big difference? It has to do with the black line. They're metals, yeah. So they're going to be, as you said, 2+ or 4+. They're going to always be plus, okay? The metals only do positive charges. So carbon is the only one that I said was 4-. Is silicon ever going to be 4-? Probably not. I'm not aware of a compound where that even comes up. So naming type 1 compounds is quite easy. Before I forget, we end at 3:50. Okay, good. I'm not behind. You guys were behind on Tuesday. You're going to end up ahead. This is exciting. Anyway, so actually you're both behind, and that's my fault. The way we name type 1s is very simple. You just say the name of the metal, put a space, and then the name of the anion. You don't ever include the charge. So sodium chloride, and you change the ending of the nonmetal to "ide." Aluminum oxide, silver bromide. Okay. Very, very important. So important, I'm going to put it in red. What must be true about all ionic compounds? Okay. The total charge of a compound, of an ionic compound, must add up to what? 0. Good. Does that look red to you? It's much redder on my screen. Anyway. So the reason I bring that up is because that explains why NaCl is NaCl, but aluminum oxide is Al2O3. So you can remind me, please, aluminum is what charge always? +3. So if I have two aluminums, and again, these are the ratios. So for every two aluminums, that's what charge? 6 plus. But oxide would be what charge? 2 minus, good. So if I have three of them, the total charge adds up to 6 minus. Okay. So please make sure that you always remember that. That will be key when we get to the type 2 compounds. The total charge must add up to 0. Also, what can have different charges? Only cations. The anions can never have different charges. Okay. So in other words, as I said, if chlorine is negative charged, it is always -1. Never an exception that I am aware. I need to stop saying that I'm aware. I'm trying to, it's very lawyery, okay? And the reason I say that is there's always someone who goes off and does something and publishes it in a journal, and oh, look, it's 2 minus. It lasts for, a nanosecond. Okay, maybe it exists, but I'm not aware of it. Okay. Now, type 2, same naming rules except for one difference, and that is you have to include the charge of the cation in the name. In other words, you can't say copper oxide anymore because there's two types of copper oxide. There's copper with the +1 charge and there's copper with the +2 charge, and they have different properties and different reactivities. So you must be specific as to those different colors. All right, so anything that wasn't on the type 1 list, which we're at the top of page 15, anything that's not on this list is type 2. So copper wasn't on that list, so it's type 2. So Cu plus is the copper 1 ion. Cu2 plus is the copper 2 ion. Sometimes I put a space, sometimes I don't. Depends on how I'm feeling that day. All right. And so we just have to add the name of the charge. The ending of the ions are still the same. They still end in "ide." So this is called copper 2 oxide. Why is it called copper 2 oxide? Yeah, exactly. You have to look at two pieces of information. Number one, the charges must add up to 0. And the oxygen must be 2 minus. So by default, copper must be 2 plus, right? To cancel out the 2 minus. Chromium 3 chloride, because the 3 chlorines are each -1, so the chromium must be +3. Does that make sense down here for chromium 3 sulfide? The sulfurs are -2. There are 3 of them, so they are a total of -6. So if the total of the sulfides is -6, the chromiums must add to +6, and so therefore each one of them must be +3. Yeah, they don't ever do I'm +4 and you're +2 or something like that, typically. Okay, so let's look at, I'm sorry, I didn't write that down, but I think we're all fine by that. Let's look at naming these 3 then. Well, let's not do chromium. I'm tired of chromium. No, I'm going to stay with it. Sorry. The 3 chromium oxides. These 3, to my knowledge, all exist. I'm certain that the last one exists, and I'm quite sure that at least one of these 2 on the left exist. So they are all going to be named chromium something oxide. Agreed? The only thing that varies is the charge. All right, so what's the charge of the first one? That should be pretty easy. Yeah, 2, just like this was copper 2 oxide, oxygen is 2 minus, so the chromium, the 1 chromium would have to be 2 plus. The most common mistake people make is they say, well, there's only 1 chromium, so that's chromium 1. That's not right, correct? It's the charge. Similar to chromium 3 sulfide, this would be chromium 3 oxide. It is the most complicated of these three, because going by the exact same logic, the total charge is 0, 3 oxygens add up to -6, the 2 chromiums must add up to +6, each one must be +3. And then this one, which we sometimes use in organic chemistry, but is quite dangerous, is chromium what oxide? Yeah, there's only 1 chromium and the negatives add up to 6. So this is 6 plus. We can go as high as 8, to my knowledge. For example, I don't know if you've ever, I don't think this element is on the list to memorize. OS. OS is called osmium. Most people call this osmium tetroxide, and most people call this chromium trioxide. Why is that technically wrong?
Those are not both.
Yeah, they're not nonmetals, but a lot of people don't care anyway, and so historically they do it. But that shouldn't be technically called osmium tetroxide. It should be called osmium what? 8, because the 4 oxygens would be 4 minus. That stuff will kill you real quick, so you stay away from it. Sadly, it's also extremely useful. Will we have any at Rio Hondo? No, killing my students is not considered a good practice. Okay, I've never even used it myself. Let me give you a weird one real quick. Let's see if you can figure this one out. You probably won't, and that's okay. This is not one I would ask on an exam. But here's a very weird case. And the one thing I want to ask you is, why is it weird, and what's the problem with that? What are the charges on the iron? The total negative is 4, right? I'm sorry, 8, -8, right? 8 divided by 3 is 8/3. So the temptation is to call this iron 8/3 oxide, but that can't work because charges must be whole numbers. The name of this one is iron, and you don't need to know this, 2,3 oxide. You sometimes see these. What does that probably mean? Any guesses? It's a mixture. Some of the irons are 2 and some of the irons are 3. Okay. I'm never going to give you a compound like that because that would be evil. Okay. But this is an important compound. And in fact, I think this is technically what rust really is. Some people write Fe2O3, but I think rust is really Fe3O4. So it means some of the iron is 2 and some of the iron is 3. You rarely come across those, but if you ever see this, especially if you're taking like a physics, there's a materials class. If you ever do material science, you might run into that. Okay. So now you know, and you may forget it for now. All right, so as I already said, total charge is 0. That's the most important mistake that people forget about, is that the total has to add up to 0. Okay. What is the name of PbO2 then? Lead 4 oxide. Very good. You have to draw the lines above? No. In fact, I thought it looked ugly, so I got rid of it. Doesn't matter. Okay. So let's look at these 4 examples, please. First of all, let's decide if they're type 1 or type 2. So barium, yeah, it's in group 2, so it's type 1, right? Group 2 of the periodic table, so it's type 1. This one right here with aluminum. Does aluminum make more than one charge, or is it always something? It's always 3+, so it's a type 1. So that means you don't need to put the Roman numeral. How about titanium? Group 2. It's a type 2. Good. Because it is it can make more than one charge. And then vanadium. Yeah, pretty much anything in the transition metals, excluding zinc, cadmium, and silver. Some people would fight me on that and say, well, what about scandium? Well, who cares about scandium? I don't care about scandium. Okay, so these don't need Roman numerals in them. It's just the name of the metal, space, the name of the anion. So what's the name of this, please? Barium. And then oxygen becomes oxide. Very good. This one. Yeah, and I picked that one in particular because this is another one people miss a lot. Anyone guess what people tend to, if you ever tutor Chem 120, what's the big mistake people make? Instead of calling it nitride, they'll accidentally call it nitrate or nitrite. Yeah, okay. Because, you know, the word nitrate gets used a lot more than the word nitride. IDE means just the element without oxygens on it. Nitrite and nitrate have oxygens in it, right? So IDE, no, those. How about this guy? Titanium, we have to look at the chlorine. Each chlorine has what charge? 1-, so we've got a total of -4. So the titanium must be +4. Good. I think some people call this tickle, but I don't want you to call it tickle, please. It's a very important reagent in some modern organic chemistry reagents. Okay. Or tickle 4. Anyway, this is, by the way, sadly, the most entertaining when students go wrong, because I've seen some such horrible answers, hilarious answer like, oh my gosh, I have a list, you know, it's like, oh, we won't even, you know, people just make up words that make no sense, and it's hilarious. Anyway, you don't want to end up on the list. This is the hardest one probably of all of these. So what is V? V is vanadium. We don't talk too much about vanadium, but it's important. 5 oxygens would be -10, and since each of these are equal, what would they have to both be? 5. So it's vanadium 5. Yeah, very good. Oxide. Excellent.